There is a disease where 1/3 of patients have uncontrollable symptoms because no treatment available works for them. The NIH spends $300 million a year on research of this disease, yet it is still the fourth most common neurological disorder in the United States.
Epilepsy is a huge issue worldwide. Generally, sufferers have no idea that a seizure is about to occur, and things that we take for granted, such as driving cars, you really can't do if you have epilepsy. Now, we intended to develop a device which sits in your ear, and it should analyze your brainwave data and predict whether a seizure is about to occur. And we want to alert the user on their smartphone so that they can take precautionary action. Over the past 10 weeks, we set about designing this product. We did everything from developing our own firmware, designing custom PCBs, and even mechanical design. And the end result was this, something which is 1/3 of the size of the closest competing product.
So what we implemented was a high-resolution 24-bit analog-to-digital converter that specializes in EEG data. We've also implemented a microcontroller to process all the data, as well as a 4-pin header that interfaces with our electrodes. And on the reverse side, we have our Bluetooth 2.0 module to wirelessly stream that data to a computer or a smartphone. And lastly, we implemented a lithium polymer battery to improve portability.
So here is our earpiece. It's made out of a hard resin, and it has 4 electrodes at very specific points. All that data is sent down through these cables and into our device, which now comfortably sits on a headband. Let me show you how it works. There it is.
Once the earpiece has been inserted, we can then connect it to the system and start to stream the data. First of all, we have to disable several of the channels because we're only using the single channel in the left ear. Then when we start streaming data, you'll see the data appear in real time on the graph on the left. Now you'll notice that the amplitude is quite low, so we'll adjust the scale to be 50 millivolts per division, and now you can see that we've got a much cleaner signal. Also notice that we have a lot of high frequency noise, so we'll add a bandpass filter to filter out some of it to make the signal a bit smoother. Now a good signal should have a fairly low impedance, and we've managed to attain an impedance of roughly 10 kiloohms, which is actually quite respectable. Down on the bottom right, you'll also notice that there's an FFT plot, which shows frequency on the x-axis against the amplitude. And this is really what the software team will be dealing with when doing their analysis.
The software development process was subject to many speed bumps and U-turns. As of yet, very little research has been published on the topic of seizure prediction with single-channel on-scale EEG. What's more, we do not have any in-ear EEG data available for analysis due to our concurrent development with the hardware team. In order to eventually move on to prediction, we decided to focus on an intermediate step of seizure detection. This, in combination with an infrastructure for storing pre-seizure data upon seizure detection, will hopefully enable us to accomplish seizure prediction at a later time.
Many different approaches were taken in realizing the classifier. In order to produce a model that would be highly specialized for the task at hand, we started pretty much from scratch. Previous implementations spanned a range of classifier primitives and incorporated features that had been optimized for multiple datasets. The final implementation used a bagged SVM model with stochastic feature vector update and adaptive feature space reduction.
I'm going to show you the classifier in action. The first step is to parse the dataset. Before we run the data into the classifier, we need to pre-process it. This consists of low-pass filtering it to 100 Hz and decomposing the signal into the following bands. Now we extract the training set features and we assign random permutations of the windows to the different SVMs. Then we extract the test sets features and train the classifier. Now let's simulate some real-time data going into the system. We're going to feed segment 5 into the classifier and plot the output. Now the top plot shows the seizures as labelled by the dataset, and that plot will go red when a labelled seizure appears, and on the bottom it'll go red when a detected seizure appears. So as you can see, the top plot has just gone red. That means there is a seizure present. The lower plot hasn't gone red yet, and there we go. So it's just detected the seizure. It's about 5 seconds late. Doesn't really matter too much, because as long as we send about 20 minutes before, 5 seconds doesn't matter too much.
An important milestone that we accomplished is setting up a data storage method in the cloud so that we can collect important patient data we can share with doctors, in addition that we can use for our own analysis in creating a seizure prediction system later on. Our database is set up to be variable so that if we want to include extra information later that we find useful while recording data, we can easily add that information without losing any previously accomplished data. So that database is set up so that on the event of the detection of a seizure, we'll send a buffer of about 20 or 30 minutes of seizure data into the database. This happens automatically. And this will be really integral to our analysis and understanding the disease and how we can predict when it's going to occur.
Now that we have a seizure detection classifier implemented successfully, along with a database to store the pre-seizure data, we can move on to the task of seizure prediction. Very important that we have patient-specific data in predicting seizures. This is because the prediction of seizures is a very difficult task, so we need each iteration of the algorithm to be specific to each patient.